Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a third video in a series on graphing parametric equations, or their plane curves, if you will. We've just finished a video on graphing the parametric curves or parametric equations by hand using elimination of parameters. That is by far the one technique you want to use above all other techniques if you can. But what happens when we cannot eliminate the parameter? What if you have a set of equations that it's just impossible to solve explicitly for t, or to use a trig identity? And that does happen. So what's the technique? What would you do? It's much easier to demonstrate it than it is to describe it. So let's go ahead and do this. Sketch the curve without building a table or eliminating the parameter. So in this case, it would be sort of difficult to eliminate the parameter and graph this by hand, because if you tried to eliminate the parameter, you'd find that t is equal to plus or minus the square root of x, and then substituting that into sign, you'd have y equals the sine of plus or minus square root of x. Good luck graphing that by hand. So instead, we're going to go ahead and use a very unique method to graph this. What you're going to do is graph x equals t squared in one graph and y equals the sine of t on another graph. And the way that I'm going to set this up is the way that you should as well. So let me showcase this step by step. The first thing I do is I break my page into 4 quadrants. This is not an XY axis. It's just 4 different graphs I'm going to have going on here. And so I start with the upper rightmost quadrant and I move clockwise. So the upper rightmost quadrant, I'm going to graph y. So let me write that down. There we go. I'm going to graph y in this quadrant. The next quadrant, I'll graph x. I'll be my x graph. And then the next quadrant, again going clockwise, is going to be the tilted or rotated x graph. So I'm going to rotated x graph. And that will help me finalize in the last quadrant my parametric curve, or parametric graph. Parametric graph. So you can see in this case, graphing 4 things to get this one graph it's kind of much, but let's just see how it works. Notice that I try to really align my graphs as well. So I used a ruler to kind of line up my x and y axes, or my vertical and horizontal axes in all of these. And I'm going to label these. Normally I don't even bother because I just go kind of quickly. But I'm going to label these. With the y graph, your inputs are t and your outputs are y's. That should make sense because y is a function of time. Y is actually the sine of time. And your x graph, again, the inputs are time, t, and your outputs are x's. That's x is a function of time. And then I'm going to just skip up here for a moment just to showcase something. In this graph, it's going to be the final graph will be x versus y. It'll be our standard graph. Notice this y, which was terribly drawn there, sorry about that. That y is aligned with this y. So I would love, not that you can see that right now, but I would love this x to be aligned with that x. I would love it if that were the case, because then I have this graph will represent the y values and this graph will represent the x values, and I transpose them up to that parametric graph. Well, if that's x, then this should be here. Let me do this. Time. And so as time increases, I get my x values for my graph. We'll see it when I graph it out. And this reminds me that it's not really rotated, it's reflected. Here, not rotated, it's reflected. Because if you look at the axes to the right, this guy right here, your vertical axis is x, your horizontal axis is t. If I want to swap those positions, I'm actually reflecting it about this diagonal line here. And so it's kind of like drawing the inverse function, honestly. And so that's what we're going to be doing. All right, let's start up here with y equals the sine of t. Note, sine of t, and we're graphing between negative 2 pi and positive 2 pi. So let me go ahead and make sure my time values, like where I label them, are the same on both of my time axes in this quadrant and this quadrant. Okay, so let's go ahead and do that. So all I did here was just align where negative 2 pi, pi, and negative 2 pi, negative pi, and 2 pi are on the t-axes. All I did was just grab a ruler and align those. Okay. And the main reason here is just so that I keep the scaling appropriate, at least on the time axis. The y and x axes don't need to be scaled the same. That's totally fine. But let's go ahead and just chicken scratch out what the sine looks like. We know the sine does something like this. Right, so this will be my sine curve here. You could scale this slightly larger. I'm just not for some weird reason. So I'm going to do this. And same thing in this direction, right? And I'll do the same thing over here. Again, I'm just chicken scratching this, so it doesn't need to be like exact, but that is pretty good, right? So there's my sine of t so y equals sine of t. I'm done with that. There's no need for me to do anything else. Downstairs, x equals t squared. Well, I'm just going to graph a parabola. X equals t squared. When t is 0, x is 0. When t is pi, x is pi squared. So I'm going to kind of draw this out a little bit wide because the scale here does not need to be like perfect. I just want to get something done here. So I know it's a parabola. I just want to make sure it fits within this window. It's somewhat of a wide parabola. Sorry about that. I suppose I don't have to make it that wide. You know what? I will make it a little bit taller. There we go. All right. And I'll make this one over here a little bit taller as well. It's supposed to be a parabola, not pointy, but just kind of chicken scratching. So terrible, terrible, terrible looking graph. Sorry about that. But you get the whole point. So I draw in a parabola. It's not a huge deal. Okay. I only need to draw it in between time equals negative 2 pi and time equals positive 2 pi. So that's because our time is restricted. Okay. Now what I'm going to do is I'm going to take that graph. So I've already drawn, again, starting with quadrant 1, I'm doing this in clockwise order. So I've drawn my y equals sine of t. I've drawn my x equals t squared. Now I'm going to reflect that x equals t squared about the diagonal line. In other words, I'm just going to graph its inverse looking function. So I'll do it like this. I don't need it to be perfect. I just need it to be a reflected version. Again, just to let you know, you're reflecting this curve about that diagonal line that makes a 45-degree angle with the x-axis. And so when you do that, you get this parabolic curve on its side. And remember, this goes from, draw this in blue, the time axis goes from a time equals negative 2 pi all the way up to time equals positive 2 pi. Halfway here is pi, and halfway down here is negative pi. All right, this is time 0. Having done all that, seems like a lot, doesn't it? Having done all that, I will now start graphing. How the heck do you graph based upon what I've just done? Well, I now know that at time 0, the y value is at this height, and the x value at time 0 is here. So y value is at this height and the x value is right there. So I now know where to start my graph. And as time increases to time pi over 2, the y value will increase to a height of 1. And as time increases to a time value of pi over 2, the x value will increase to that point right there. So essentially what you have is the following. Let me make sure that I don't screw things up too much. You have this beautiful curve doing something like this. Okay. And then as time increases from time pi over 2 to time pi, the y value goes back down to a height of 0. So it's somewhere along this axis right here. And the x value continues to increase. At time pi, the x value should be somewhere about here. So let's go ahead and draw that in. Looks something like this. So it probably did something like this. Okay, so we know the path of travel is doing this. And now let's go beyond time equals pi. At time equals 3 pi over 2, the y value should be -1. Let me just showcase that. It should be at this height right here. And at time 3 pi over 2, the x value should be right about there. So we're targeting where they cross. So let me go ahead and erase these lines. There we go. Plot it right there. So it did something like this. And again, the path of travel, just kind of doing this. And then finally, at time 2 pi, our y value is at the axis. So, and our x value is way over here, so it's something like this. All right. One thing you should note here are the x values themselves. So at time pi over 2, remember the x value is the square of that. So this is actually an x value of, I'll label it here, pi squared over 4. This x value was at time pi, as I recall. Yes, it was. And so that would be the x value for time pi would be pi squared. This is time, let's see, what time was that? 3 pi over 2. So remember, x is time squared, so it's 9 pi squared over 4. 9 pi squared over 4. And this is time 2 pi, so that'll be 4 pi squared. So while it may look like a regular sine curve, it's actually not. It's our scale that we're choosing that makes it look like a regular sine curve, but it's totally not a regular sine curve. Sorry. Now let's see what happens when you go in the negative direction. So at time equals negative pi over 2. You may think like, oh, it's just a sine curve then, so let me just retrace this, or let me continue it this way. Don't. Because first of all, your x values don't go that way. Your x values remain in this direction. All right. So let's see, at time negative pi over 2, the y value is going to be at a height of -1 there. At time negative pi over 2, the x value is going to be right about there, where they cross, basically. It's going to be a reflection, but there you go. So let me go ahead and draw that in. It's going to be something like this. So again, at time negative pi over 2, so between negative pi over 2 and time 0, it's the particles traveling in this direction. That's what it's going to look like. Now you can use the symmetry of this to really help you out, but I'm just going to do one more step to showcase it. At time negative pi, the y value is 0. And at time negative pi, the x value is right here. So I kind of angled that to make it work, but your y value is 0, your x value is right there, so it looks like this. And you could probably guess it's going to look like this. So that's what it looks like. This point right here corresponds to time negative 2 pi. And then this is time negative 3 pi over 2. This intersection point is time negative pi. This is time negative pi over 2. This is time 0. This is time pi over 2. This is time pi. This is time 3 pi over 2. And then back to this point, which is also time 2 pi. That is a full graph using a very unique method of graphing. Now, not a lot of people like this method. I completely understand that, but it is kind of a nice graphical way of getting this. Some other people will actually plot values, build a table of values, and that's perfectly fine. You could do that as well. But I'm just telling you that this, once you become proficient with it, is a really nice way of graphing parametric curves if you can't eliminate a parameter. Let's go ahead and do one last example. Sketch the curve, again, without building a table or with eliminating the parameter. Don't do either of those. You can't do that anyway here. One thing you should note, time is going to be positive, okay? And that's it. That's all we have to note. Time is non-negative, I should say. So let me break this piece of paper into 4 quadrants and then draw in all my axes. There we have it. Took me a few moments, nothing really crazy. We're going to go ahead and graph y in this one. Let's go ahead and do that. And if you note, even the y itself is going to be somewhat challenging to graph, right? The thing that you have to realize about graphing y is equal to t sine of t or x is equal to t cosine of t is that the role of this coefficient here, t, the role of that is like the role of the amplitude. So as t increases, the sine curve, quote unquote, gets louder. And that's a good way to think about this. So what I'm going to do is currently just go ahead and plot time values that are easily used in the sine or cosine function. So basically 0, pi over 2, pi, 3 pi over 2, and so on and so forth. I'll probably graph out. Actually, I think a single full cycle will showcase the pattern that we're looking for. So let's go ahead and do that. I'll pause the video and plot those points. The next thing I'm going to do is go ahead and graph the line y equals t or y equals x, if you want to consider it that way. And this is just a little trick to graphing when your coefficient of your sine or cosine function is another function like t or t squared or e to the t or something like that. It creates a boundary of what your y values are going to be. So I'll showcase what I mean by going ahead and just graphing out y is equal to x. I'll put in a 45-degree angle here because y equals x is gives you that 45-degree, and then I'll showcase this. And honestly, this is not really part of the discussion or this lecture on how to graph a parametric. It's just you may never have graphed something like y equals x sine of x before, and so it might be a good idea to talk about this. Now, you know, normally the sine curve does this thing. It goes up, it comes down, it goes down, it comes up, okay? However, what's happening here is that our amplitude is guided by these lines, y equals t and y equals negative t. So in reality, you get something that looks like this. So the maximal value at pi over 2 will be here. We're still at 0 at a height of negative, or at time pi. At time 3 pi over 2, the height is down here, and at time pi, 2 pi, sorry, it's there. And so you kind of see it's a little bit squished in here, but it looks something like this. And it gets even louder. When I say louder, it's an amplitude. So it gets louder as time goes on, ... Okay. And you could do the same thing with the x equals t cosine of t curve. I'm just going to go ahead and quickly graph here the y equals t I guess in this case, I'd call it x equals t and x equals negative t. So there you have that. And then you can see normally the cosine curve does this thing where it goes down, comes up, goes back up, right? But really what's going to happen is that you can plot the points at 0, pi over 2, pi, 3 pi over 2, and 2 pi. And the maximums and minimums will follow the guides of these two asymptotes, I guess you can call them, even though they're not. So instead of being at a height of 1 at times 0, because the coefficient is t, it's going to multiply that 1 by 0. And at time 0, it'll be at pi over 2. At time pi, it'll be, at time pi over 2, it'll be at a height of 0. At time pi, it'll be at a height of normally -1, but it's negative whatever this value is, which is pi technically. Time 3 pi over 2, it's back at 0. And time 2 pi, it's all the way up here. So it looks something like the following. Let's see. So something like actually this. And it climbs all the way up to there. Okay. And then it just repeats this continually. It gets louder and louder as time goes on. When I say louder and louder, I just mean that it, again, the curve gets broader and broader, more amplitude as time goes on. And now what we're going to do is reflect this curve, because remember, this one right here is time versus x, and we want to get x versus time. So I'm going to reflect this curve actually about this line right here, y equals x. So we'll reflect it about that line, and that's going to be a little bit challenging to read, but I'll try my best to do it. It looks like this, and then obviously it gets more and more as time goes on, but that's what it's going to look like reflected again about this line, y equals x, or in this case x equals t. All right, and now we have everything we need to actually graph the curve on the Cartesian coordinate system. This is probably the hardest one you'd ever want to graph by hand, honestly. But you could see the y values, I'll showcase it here actually. The y values start at a value of 0, they grow, decay, and grow, and decay, and so on and so forth. Simultaneously, as the y value started at 0, the x value started at 0, but they grow slowly, just like the y values grow slowly, and then they go over as the y values decrease. So maybe I should be very careful with this, because I'm seeing that it will be a bit tough. This one is going to be a bit tough. So at time 0, y is 0 and x is 0. So I'll start with that. At time pi over 2, the y value is going to be basically at pi over 2 times 1. That's our y value, so it's going to be a y value of pi over 2. I'll just mark that in here at a height of pi over 2. But the x value at time pi over 2 is going to be 0. That's, you can see it here as well. So it's going to do something like this. Okay. And then after pi over 2, by the time we get to pi, the y values are down to 0. But by the time we get to pi here, the x values go down to pi times -1. So let's go ahead, and this is time pi right here. The x values get all the way over there. So it's the y values decrease to a height of 0, and the x values get to that point. So it looks something like that. Then at time 3 pi over 2, the y value is here. And the x value, I should have labeled these beforehand, but that's the x value right there. So we are going to basically ramp right back to this. And then at time 2 pi, the y value is at the x-axis. And 2 pi, that's right here, the x value is over here. So it looks something like that. It almost looks like a spiral, doesn't it? And then if you continue forward, at the time of 3 pi over 2, which is right, or 5 pi over 2, which is right here, the y value is suddenly super high there. It's way up here. But at the time of 5 pi over 2, which is right here, the x value is back at the x-axis, or basically the x values are 0. So it does look like a spiral, doesn't it? And so on and so forth. So it probably is a spiral, to be honest with you. I'm so curious, I'm actually going to graph this out. And I'm back here in Desmos. I don't need this 2x squared minus 1. You can see that is actually, I've just graphed it out, t cosine of t, comma t sine of t. I'll have a video on how to do this. But you can see that we are definitely carving out a spiral. And so our graph was pretty accurate. Yeah, not too bad. Now, like I said, by hand, that is an incredibly tough graph to do. So I don't blame you if by hand you just say, man, that is really, really tough. Because honestly, it is a challenging graph to do by hand. There's nothing wrong with that. The vast majority of what you're going to be doing, though, is not something like that. You're going to be doing elimination of parameters. But this is just a good method to see. Not that I require my students to do it all the time, but is a great way to derive the graph of a complex looking parametric curve. All right, that does it for this video. In the next video, we're going to find parametric equations for linear equations handed to us in Cartesian form.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.